Now?
Don't start it yet. First set this thing. Now come here.
No, wait. It's maybe not working. And it is working. Okay. Alex, can you just like open YouTube on your phone? Let's check if the audio is working. If it works, just open your phone.
Quinta vez que te hablo. Desgraciado. Entonces, vinimos por Alexei.
Like long click, it will keep doing it.
Alexei, ¿vine por Alexei o por la pizza?
Wait, can like you
Yo, ¿vine por Alexei o por la pizza? What do you think?
I'm measuring it. So be precise.
I told you. Yeah, I told you.
This is working. Can you hear? Yeah. As soon as you go and I'm just looking, so I think this works. That's your phone, right? Yes.
just see if everything's really
Yeah. Pablo! Santos! Your presentation. Where? Outlook? Okay. I don't know, I didn't check.
Rápido. Pero cuando te estás deteniendo pensando que vas a escribir y no estás escribiendo bien.
Ferme la porte. Ferme la porte.
Estás intentando
Pour que les personnes ne sortent pas.
es asociado con algo negativo. En este caso, como
C'est
el
moins...
contexto es eso. Y también
C'est psychologique.
tiene el cuarto de tiempo.
Ah, tu as un odorat trop fort. Tu as un odorat trop fort. Je te jure que c'est que toi. Personne n'a dit que... Vomir. Je t'en supplie. Je t'en supplie. Everyone is sortant. Everyone is sortant. C'est que la porte est ouverte.
I remember when you first told me you have to give a looking for analysis.
O sea, quieres ver todo lo que es el problema.
I kind of just try to do complex analysis without doing complex analysis.
Básicamente, la primera parte
We'll
es
talk a lot about complex analysis.
o sea, la 1 tiene X1, X2 y X3. Y aquí está usando X1, entonces el clash existe entre 1 y 2.
It will be fun.
Es todo.
I'm excited
la
for the
primera
complete
parte.
this theorem because I've never seen the proof.
Ciertos
I've
errores
never.
pueden pasar en este caso.
It's not a very.
No hay desorden en cuestión de primero y después. Todo lo que tienes que hacer.
It took me a while too because it's like
En la segunda parte solo es asegurarte de que el clash no suceda. Pones esos
there's still some, I would say, some limitations I will tell you about. The guy used a very system of arithmetic, very reduced, so, but it's fine.
What's this?
I can already go.
No.
Can you set the YouTube link on my website?
Okay. صرت لوالديك؟ لا مازال صرت ليك صرت في ما سوسايتي صرت شي صرت تشوف جنرال
Well, I don't have any. Well, I have.
صافي اتفقتوا على تصوروا
Well,
وي زعما غير ما مشى تصورش عاوتاني استاذ Je pense que ça fait besoin. Maybe too. Should we take the chairs?
Linear algebra takes a lot of time, but I
شكون مستحيل؟
not necessary, but like I still.
I think discrete numerical this is not the mathematics class, it's just like engineering.
Numerical method.
Commençons.
Because there's no proofs.
Yeah. Should I take this week? Like what like I've heard it's interesting, but like what?
Honestly, it's torture.
صافي
Yeah, I know.
صافي جوج كما تقول لا
I kind of having. I know.
guys. So with Charles, can you take seats please?
Alex, le dije al ruso, si te va bien, el cerebro te lo oye. Si te va mal, primero me traiga después te ayuda.
No. Oh, this chair was only for you. Come on, sit.
I was really hoping that you.
So hello everyone, hope you're all doing well and welcome to the last event of the semester and of the year with the Mathematics Society, which is the undergraduate seminar 5. So again, welcome and thank you very much for all of you that came here. And I know that a lot of you don't really...
You're doing my presentation.
Yeah, so I was saying, a lot of you don't even know what's really an undergraduate seminar, so I'm just going to give, I would say, a small intro. And the undergraduate seminar initially had, I would say, a different story. Initially, before that Construction University became Construction University and the era of Jacobs University, math majors had a course that was called the undergraduate seminar. And basically, they had to do a sort of research in their second year, but Serge Bell came, math major became MMDA, and so on and so forth. But we decided to revive it. And the point is that us, the Math Society, we provide 2 to 3 students selected each semester to do their own research project, where they are supervised by us, the course of the Math Society, and professors who review the paper later, including Professor Keva, including Professor Ivan here, and including Professor Nikolai. And yeah, that's pretty much what is about the undergraduate seminar. So if you think that you have research projects in mind, or if you have anything, or you're willing to do your first, I would say, real project, you are free to come to us, you're free to apply, and the QR code will be there at the end. For today, we have 3 seminaries, 3 students that were selected for the last undergraduate seminar of 2026. We have Alexei, who will talk about Gödel's incompleteness theorem, when mathematics met its limits. We have Tahbiri, who will talk about reaching a possible agreement, the Paxos consensus protocol. And finally, Pablo Santos Guerrero, who will talk about the fundamental theorem of algebra and the geometry of zeros and poles. As you recall, just want to mention that all the students that are going to present today wrote their research paper that are getting reviewed currently by the professors. So if you would like and you would be interested in knowing more about each of their subjects, you are free to read the papers that would be all available in our website. And yeah, that's pretty much what I have to tell you. Hope you're all ready and be ready, because in a few minutes we will start with the first talk of today given by Alex on Gödel's incompleteness theorem. Thank you very much, guys.
Are you actually gonna yap?
I think it correct, right? That's fine. One slide is fine.
All right. Good evening, everybody. Thank you very much for having your evening here today. math society. It's a pleasure for me to be for being selected for that project, because it took me a while to get the paper done and to prepare to get to the topic and everything. And I want to ask you one question. If you consider mathematics, can mathematics prove everything that is true? Or is it possible that such precise system as mathematics has limits? Well, that's basically what we're going to talk about today. We're going to talk about mathematics and its limits. Let's consider this slide and the statement that is written here, which says the statement on the slide, on the next slide, is false. Okay, let's move to the next slide and see what's there. And this said that the statement on the previous slide is true. So is the first statement true or false? Well, if you consider that, if the first statement is false, then the second one, which states that the first one is true, is also false. But then we just said it's true. That's a contradiction. So the more you start reasoning, the further you start reasoning, you understand that there's always be an infinite loop. When you start asking yourself a question, can mathematics avoid contradictions like that? And before I give you that answer, let's just go back a bit back in time and see how mathematics has evolved until the point where it firstly reached that question. It all started in ancient Greece and with the development of logic as a subject of formal reasoning, of precise, basically the whole geometry from just a few postulates, which has become the standard for mathematical certainty for more than 2,000 years. Then, many centuries later, precisely in the 17th century, the German mathematician Gottfried Leibniz pursued a very interesting idea. He said, let us take purely systematic system, purely conceptual system of reasoning, where we will not argue, we will just put everything to the symbolic system. And he called it the calculus rationator, which basically means the universal calculus of thought. And these ideas of mechanical derivations, the idea of conceptual reasoning has received the influence many centuries later and has influenced many great mathematicians. But in the 19th century, something started going, interestingly, to the different direction. Maybe you know that you are mostly taught in school that if you have a plane, and if you draw the line on that plane, and then you put the dot on the plane, the point, then you can only draw one line through that point which is parallel to the first one. But in the 19th century, the Russian mathematician Nikolai Lobachevsky showed that there is some other things. That there is possible to create a space where you can draw infinitely many such lines, and which is now called the non-Euclidean geometry, or precisely Lobachevskian geometry. And the idea is that the axioms define the structure of space. So what is true in the Euclidean world may not be true in the Lobachevskian world. Then the foundations started to tremble, because as the advancement of science and mathematics showed that the foundations that people had were not enough. For example, Fourier showed with his smooth series that could represent different oscillations and discontinuous functions. Then the Cauchy, Weierstrass, and Bolzano worked on the precision definition of limits. Then the Cantor's set theory, who eventually arrived to paradoxes, and Dedekind and Scutz, who worked to define the real numbers with very rigorous precision. And then we said, maybe mathematics should be symbolic. Maybe everything should be represented only using symbols. And that was the answer to that, because George Boole in the 19th century developed a system which now is called the Boolean algebra, and where he showed it through logical proposition how it could be derived. Then the Gottlob Frege worked to derive all mathematics and reduce it basically to the logical principles. And finally, Giuseppe Peano developed the whole systematic symbolic system, arithmetic system, which only uses the symbols. And now, many years later, we're still using that. Interestingly enough, when formalization started to become the idea of mathematicians, well, the pure formalization of all mathematical proofs, of all mathematical concepts, Bertrand Russell pursued the idea, let's just formalize everything and deduce it to the formal logical principles. And he did it in the 3-volume work, the giant work, which contains around 2,000 pages, which is called the Principia Mathematica. And the precision was so rigorous that it took him almost 350 pages to prove that 1 + 1 = 2. Yet, he still encountered paradoxes. One of them is called the famous Russell's paradox. Let's just identify it for the sake of reasoning. Let's define R as a set of all sets that do not contain themselves. Now let's assume that R contains itself. But wait, if it does contain itself, then by definition it shouldn't contain itself. There is a contradiction. Let's now say that R does not contain itself. Then by definition it should, which is again the contradiction. And did you spot the self-reference, how the set references to itself? Please keep that in mind, because soon you will see very surprising facts, how we will use self-reference to derive very important truth to mathematics. And with that paradoxes that occurred through all the development of mathematics, people start asking, can we build a perfect mathematical system that has no contradictions, that can prove everything within itself, and that has the algorithm to do that? And there was an answer to that, or I would say the proposal. The German mathematician David Hilbert, in the first half of the 20th century, proposed his program, now famously known as Hilbert's program. There he wanted to put all mathematics to the very solid foundations, to secure it. He identified 3 main requirements for mathematics, such that he could make this possible. The system should be complete, such that every true mathematical statement within the system has a proof. The system should be consistent, such that the system must contain no contradictions. And the system must be decidable, such that you always can have an algorithm to derive whether a statement is true or whether it is false. The strategy of Hilbert was precisely that. He would take the complex mathematical theories, he would reduce them to the very basics, to arithmetic. Then he would secure the proof, the completeness of arithmetic. And by that, he will be able to prove mathematics in general. And for a moment, it seemed as though mathematics could finally be made certain. But this dream did not last. And it has something to do with the very first paradox we started this presentation with. Because in 1931, a 25-year-old Austrian mathematician, who basically two years before that completed his doctoral dissertation, published a paper that would change mathematics forever. And this man was Kurt Gödel. And the paper title of his work is On Formally Undecidable Propositions of Principia Mathematica and Related Systems 1. It's a very unpretentious title. But the contents of the paper and what Gödel has concluded has changed it forever. He proved that Hilbert's dream was impossible and that the perfect mathematical machine could never be built. He did that precisely by his now famous 2 incompleteness theorems. Let's consider them in detail so you understand better what he did exactly. The first theorem says that any consistent formal system within which a certain amount of elementary arithmetic can be carried out is incomplete, such that there exist statements within the system that can neither be proved or disproved. In other words, they are true statements that cannot be proved. And the second theorem, which said that for any consistent system within which the same amount of arithmetic can be done, the consistency of that system cannot be proved by that system. In short, the system can be consistent, but it doesn't know it is. And so with these results, with these openings of Gödel, the dream of Hilbert, the idea of Hilbert to formalize everything, make everything provable, make everything predictable, it shattered. But how did Gödel do that? Because we're not talking only about the results. We want to see what exactly he did to make the things possible. And before we actually move to the proof, so that you can see the logical reasoning, I want you to focus on some preliminaries, the toolkit that Gödel used for his proof. And these are 4 of those: the formal system, arithmetic, Gödel numbering, and the diagonal lemma. The first one is the formal system. Let us give a bit of definition here. The formal system, you can consider it as an abstract framework from which you can derive all deductive conclusion based on the fixed set of rules. And the formal system usually has 3 main elements, which is the language, the formal language. This is just a symbolic vocabulary. And every statement within that system is written only using that vocabulary. The axioms, these are the starting assumptions. The assumptions that do not require any proof. And finally, the rules of inference, the rules of derivation. An example of that is the piano arithmetic. If you have ever seen the piano axioms here, the most basic piano axioms here, you will understand what I'm talking about. We have the formal language, we have the derivations, and we have axioms by itself. The next thing is arithmetic. It's basically the mathematics of natural numbers and its properties. The building blocks of which is, of course, numbers, the operations, the relations, quantifiers, and expressible statements that can be derived from that. You can derive 2 + 2 = 4, or there exists an x such that x + 1 = 3. And the important thing about that is that using that arithmetic, the system becomes powerful enough to express natural numbers and its properties. Now we come to the most interesting part, I would say, in terms of preliminaries, which is the Gödel numbering, which is the technique that made the proof possible. And the Gödel numbering is basically the encoding. If you know how data is now encoded by computer, ASCII code, UTF, and everything, that's basically the same, because Gödel's idea influenced that. We're going to take the symbols of our system. You can see them on the left here, and we're going to use them to encode them with unique numbers, such that 0 is encoded as 1, the successor is encoded as 3, not is included as 5, and so on. But the problem is that Gödel used a very primitive system. He wanted to use the very basics to conduct his proof. So to make it clear for you and to give you some examples, we want to extend this table with 3 more elements, which is equality, addition, and multiplication. And with that, the sequences of symbols will become, will use the method which is called unique prime number factorization, which is basically the fundamental theorem of arithmetic. And as a result, every formula and proof will have a unique number. And given a sequence of Gödel numbers such that, and 1 from nk, our sequence will become something like that. So the basis of each value will be actually the prime number, and its power will be the encoded value from our table. And with that, arithmetic can now reason about its own formulas. Let me give you some examples how it works. Let's try encoding 0 = 0. The formula 0 = 0 contains 3 main elements, which is 0, equality sign, and 0. So 0 corresponds to Gödel number 1. Equality corresponds to Gödel number 15, right here. And 0, once more, corresponds to Gödel number 1. And the Gödel number of the formula will be something like that. So this huge value, extremely huge value, will only uniquely represent 0 = 0. Let me give you a more complex example. Let's try doing 2 plus 2 equals 4, which we presented earlier. Because in the table, we don't have the encoding of 2, 3, 4, 5, and so on. We have only 0 and the successor of 0, which is basically 1. So to represent 2, we need 2 successors of 0. And to represent 4, we need 4 successors of 0. That's why our final formula of 2 plus 2 equals 4 will look something like that. And it will expand to 13 symbols here, such that S is encoded by 3, S one more time is encoded by 3, 0 is encoded by 1, plus is encoded by 17, and so on. And the final Gödel number of this formula will look something like that. Again, a huge value. And when you ask the question, why does Gödel number matters? The idea is that now the formulas become numbers, and the arithmetic can talk about those numbers. And as a result, we are able to construct a very important thing, which is a self-reference. Remember when I asked you to remember it, to take it into consideration when we did the sets of all sets proof. And to do that, to do the self-referential statement, we need a thing which is called the diagonal lemma, which is the helping theorem that enables us to construct the self-referential statement. Because if you take any human language like English, German, any language, we can construct a sentence like, this statement is true, or this statement is not true. But in mathematics, it's not possible, because mathematics operates with numbers. So we need to create a property with a sentence, such that the sentence will refer to itself by its own Gödel number. And the Gödel number, you can consider it as ID. I don't know why it's a bit shifted, I guess. Yeah? And now we want to go to the proof. With all those toolkit considered, we want to go to the proof of the theorem and see how Gödel exactly showed the limits of mathematics. Let's firstly consider a formal system S. Let the system be effectively axiomatized. Let it be consistent, such that it doesn't prove both contradiction and the statement, right? So it does not have any contradictions. And it's powerful enough to perform basic arithmetic. That's why we talked about the Gödel numbering. Let it be the formal system, and let's define a sentence, a system or a statement in that system which is called G. If the statement G is provable, we will write the following predicate, or the following function, you can call it like that. The provable in system S with the Gödel number of G. If G is not provable, let us write not provable in system of S of the Gödel number of G. And now we want to construct the self-reference, such that the G says of itself, I am not provable. In that case, you can read the statement as G is provable if and only if S cannot prove G. Now let's make an assumption. Let us suppose that S proves G. Then G is provable, but because it's Gödel number, it has Gödel number connected to it, so it's provable. But we earlier defined that G is provable if and only if S cannot prove G. So G is not provable. So we reach two opposing conclusions, that G is provable and G is not provable, which is a contradiction. And by that we can conclude that S does not prove G, which is basically our first statement. So this statement is true, but it is not provable. We can actually end the proof here, but let's consider another case. Let's suppose that S proves not G. If G was not provable, then not G is provable. In this case, if G is provable, then S proves G. But we already concluded before that S does not prove G, which is a contradiction once again. So the S does not prove not G. And as a result, S is incomplete and undecidable. And by that proof, but very precise and very short, you can consider, because we managed to put it in one slide, proof what we achieved. we managed to formalize the self-reference. We managed to show that truth is not equal to probability, such that there are true statements that cannot be proven, and that the limits by itself of the system, they are provable. And why does it all matter? Because the Gödel's idea, the Gödel's conclusions, the powerful conclusions that he achieved almost 100 years ago, they're not only relevant for mathematics, they're relevant for many other fields, such as, for example, computer science. Because the whole theory of computation, of computability, is built on that. The artificial intelligence, where we start asking the question, can machines replicate human consciousness and behave like humans? And philosophy, where we question the nature of truth and the limits of human knowledge. One of the greatest scientists ever lived, the father of computer science and artificial intelligence, Alan Turing, used the Gödel's ideas and Gödel's conclusion in his work, where he proved a very important problem, which is equivalent to the Gödel's proof for computer science, which is the halting problem. The idea of the halting problem is very easy. Can there exist an algorithm such that it can determine that an arbitrary program will run forever or stop? And in 1936, Alan Turing proved that this algorithm does not exist, such that some problems have no algorithmic solution. Artificial intelligence. If you consider artificial intelligence as a large formal system that has part of arithmetic in it, it will mean that it will be applied to the Gödel's proof. And there will always exist truth that AI cannot derive. And this is not a bug. This is mathematical certainty. And you cannot fix that by adding more data to it. If you consider writing a prompt for your favorite LLM as well, consider how your text is then encoded. Consider that your text will be eventually split into smaller sequences of information. And then this text, each smaller sequence will be given a unique number. That's exactly what Gödel did 100 years ago. And then we start asking deeper questions. Can intelligence be fully formalized? Are humans different from machines? And is knowledge inherently incomplete? I put the photo of Roger Penrose, a famous British physicist here, because he was the one who argued that human consciousness is something more than a set of algorithms. And what about our reality? A big question, right? Is it true? Is it real or not? Eventually, it was interesting because for many decades there was a theory, a hypothesis, I would say, that our reality is actually a hyper simulation created by some advanced species, I don't know, aliens or something. And the theory was very popular. If you watch the Matrix movie, you will know what I'm talking about. But 6 months ago, there was a study which was published, a mathematical study, and the study revealed that some features of our universe cannot be reduced to any set of algorithms. And the proof that those people used relied on Gödel's theorems. And they concluded that reality is indeed real. And as a conclusion, we want to say that despite the incompleteness of mathematics, it is still a very powerful tool which helps us perceive this world and work with it. But the system still has limits. But those limits still deepen our appreciation of knowledge as an open-ended journey and make it possible for us to move forward. And as Kurt Gödel said, either mathematics is too big for the human mind, or the human mind is more than the machine. Thank you very much.
Any question?
I had a question to start. First off, thank you for a very nice talk. I wanted to ask you, because you had on the other slide that there are probably some statements that AI cannot prove. do you think there are statements that AI cannot prove and humans can? Or is it just the fact that statements are unprovable by any means possible?
I would say the things that human can think about those problems is exactly what difference is from AI. That's a good question, but I'm not sure if I can give you an answer right now. It's very philosophical, you can think about it. But I guess we will know it with time. Because the technology, the pace of how technology evolves, we may soon discover things that we might never realize ever existed. And that's why your answer could be there as well. The answer to your question can be there as well.
It's definitely an existing subclass of questions that can be solved by humans, but not AI.
But not AI, yeah.
Maybe you can work on that for your next stuff.
For next
Bachelor thesis.
Actually, as a graduate of the university named by Lobachevsky, I'd like to comment on the postulate of parallelity that you presented.
Okay, sure.
Because it's, I have some corrections to that.
Okay, sure.
Yes, so I'd like to write so a bit whiteboard. Can you switch to that slide, or maybe...
People can join Math Society well.
I can use this. Okay. Then whiteboard. Correction to the definitions. So when you say this, this looks like self-reference because it was just before with two definitions. Yes. So when you say that on the Euclidean plane there is only one parallel, it's like self-reference because what is a parallel?
No, I mean that on the space only one line can pass through the point that will be parallel to the other line.
But what is parallel? What's the definition?
Oh, well, that's another thing.
That's the question. So, in Euclidean geometry, we have a statement, yes, that if we take a line on the plane and we take a point that doesn't belong to this line, then there exists a unique line that has no intersection with this one. Okay? So first we prove about the property. And then we say, as this fact is accepted, that this line is unique, and then we say, we call this line a parallel. And with this definition, parallel is well defined, because we well describe the properties, that it's the line is not intersecting the given one, and it is unique. What happens in the Lobachevsky geometry, or in Germany, many people call it hyperbolic geometry. So the assumption is the opposite to this one. And here, clearly we said, there exists a unique line. So we say there exists more than one. Okay, so the Lobachevsky statement is that assume, so we just take as a new postulate that there exist at least two lines that pass through this point. For any given line, for any given point, there exists more than one line that don't intersect the given one. And now let's see how it evolves into statements. So if we have these two lines, then we can take, so we can consider the set of all lines to this point. In particular, a line that lies here also doesn't intersect automatically, because every line that lies in between also doesn't intersect the given one. So if we have two, we have infinitely many immediately. Then, if we consider the class of all lines to this point, we will have intersecting lines and non-intersecting lines. Okay, so now basically we take one line and rotate, so make the full turn around. And then this full round will be divided into classes, intersecting and non-intersecting. And those classes, they provide the splitting of the angles, which means that those two classes have a boundary. Okay, and these two classes on the circle, they have two boundaries, definitely. So one class non-intersecting, one class of intersecting. What happens at the boundary? So I mean, some limiting position of the line such that turn down intersects, turn up don't intersect. What happens at this boundary position? So it is still non-intersecting line, because if it was, then we could turn up and still intersect. Okay, so now we have the conclusion that there is a limiting position to the right. Oh, thanks for the black color, and the special limiting position on the left. Okay, so we have exactly two special lines that we define like this.
Are they touching the line or not?
No, they don't intersect still, because if they
Why are they not part of the? Why not the same logic the other way?
they are. So we have like a circle is divided into open sets, okay, which have the common boundary, and boundary consists of 2 points. And now we analyze what happens in those points, and then we see that those points also belong to the upper class, so non-intersecting. So the upper set is closed, so it includes its boundary, and the lower set is open. So the set of intersecting lines is open, doesn't include the boundary.
Okay.
And so, by this principle, we define two special lines, which in hyperbolic geometry is called right parallel and the left parallel. So this is my comment that those lines, infinitely many, are called just non-intersecting. But parallels are those two special. So just one moment. In hyperbolic geometry, there exist triangles that are composed from mutually parallel lines in this direction, this direction, this direction. So this is a triangle which has a finite area. It can be computed in hyperbolic geometry, exactly computed, but there are no vertices. What's the question?
When you define the line, the boundary line, you said if it was touching, you could turn it up a little, and it still would be touching.
Yes.
Why not the same logic the other way around? If it's not touching, you could turn it down a little, it's still not touching.
That doesn't work.
Same logic, exactly the same logic.
Same logic, okay. Just because the line is ordered. So as long as we have the point, then there is always the point on the right. Okay. And the previous axiom says that through two lines there is 2 points lie on the line. So for every intersecting line, there exists such a line on the right. Yes, but then for the non-intersecting, there is no such principle, so we cannot specifically prove the existence. So this is it.
Thank you very much. Well, so we will now move to the second talk of the day, second talk of the undergraduate seminar given by Taha Hafiri on the irreducible consensus and the FLP theorem and Praxis protocol. Let's go, Taha. This? You can do it at the end.
I'd expect more of it. Half of it. You know, half of it. The intuition is a big problem.
Look, man,
That's two apples now. That's
You justify the piano. The thing is, when you ask the question, could AI not prove something a human could know? It's the same shit. The human couldn't prove anything AI couldn't prove. It's example. With any facts. Now that's the real question. That's the thing, you don't. But you it's into human intuition knows the answer.
so the we should accept
Hey guys, so we're starting now the second chalk. You ready? Watch me now. Okay. And good luck with that.
Sorry. So hello everyone, welcome to the talk for the FLP theorem. My name is Tam, I'm a second year computer science student. Hope you all know me already. So before I start my talk, I'd like to give a quick mention. We've all experienced Lambert's clock in our life. The reason why I'm saying this is that I'm sure that everyone has already used a laptop, a phone, a computer, anything that uses the Lambert's clock, even though we still don't know who it is. But this takes me to my next question. Have you ever asked yourself, if we take for instance, me and a friend of mine that lives in a, let's say, different country, were to buy a seat for a specific event that only has one ticket available. Let's take for instance here the next World Cup this summer, and there's a football match and there's only one seat available. And I decide, my friend and I, to click on the button purchase in the exact same second. Who would get the ticket? So this problem was sort of solved by Lampert, and he called it, he didn't really struggle to find a name for that, and he called it the happened before relationship. What the happened before relationship says is A happened before B on 3 golden rules. These rules are pretty straightforward and simple. What the first rule says is if we're looking locally within one single machine, if A was executed before B, we can say that A happened before B. The second one says that if 2 machines are communicating and one machine sends a message to the other, the action of sending the message happens always before receiving that same message. This is pretty straightforward. The third one, and Ahmed's gonna like this one, is using causality. And this is the transitive one. We say that if A is causing an action X, let me write it down for now. If A is causing an action X and X is causing an event B, we can therefore say that A has definitely happened before B. But there's a problem with this relationship. This uses the implementation of Lambert's clock, which is, I'm not going to go into detail, but uses a counter, an internal counter that increments every time an execution of an event happens. But this only gives us a partial order. What I mean by that is that when I have 2 machines, let's call this machine A, actually, let's call this machine T, and I have a second one, let's call this H. An event A happens before B, and here an event C happens before D. Within the machine T can accurately say that A happened before B, and this can be similar said by, for H. So C can happen before D. However, the two machines cannot distinguish which event happened before the other without communicating it. So we cannot determine whether A happened before C or C happened before A if we do not communicate the action. So this only gives us partial order. What we mean by that is that we only have the order within one local machine unless we send a message. So if we cannot know the order of events in two different servers, and my friend lives in a different country and access a different server, how do we actually solve the problem? This is what we call the consensus problem. And turns out, this problem is actually mathematically unsolvable. But wait, let me explain. What I mean by unsolvable is here I'm saying there's no deterministic algorithm in the world that can guarantee consensus in an asynchronous system when even one faulty process can happen. And this can be very dangerous. In 2012, a company called Knight Capital lost $440 million in 45 minutes just because their servers could not agree on the same value. So if that is the case and it's so dangerous, how do we address this problem? What do we do then? Well, to actually find a solution, let's forget about machines for a second. And let's say this talk seems pretty boring. Let's do something different. Let's propose a different activity. Let's say we all want to go to the cinema, for example. Let's go to the cinema, and I would call that an event A. If somebody doesn't want to go to the cinema, they want to do something different. Let's call that action B, and we could for example go have dinner. I know everyone is hungry and waiting for the pizzas, so it would be nice to actually have good dinner. We could propose something different. You could, I don't know, propose a third activity. I don't know. Let's, for example, go swimming. The weather's pretty nice. We could go swimming. If I were to ask any one of you guys, if we were all to agree on one activity, what would be the system we would use to actually all agree on one value?
Voting.
We'd all vote, exactly. Everyone would have to choose one activity to do, and therefore we would follow with the majority. What if, for example, theoretically, we have 7 people wanting to go to the cinema, 9 people wanting to have dinner, a lot of people are hungry, and only 1 person want to go swimming. We could then say that most of the people, the majority, want to go have dinner. We would all have dinner because everyone has to follow the majority. What happens is, not every time people can vote. Let's say 2 people fall sick for some reason. They're not dead. They can still come back at any point. But ends up, we only have 7 people voting, and now there's no majority anymore. And even if it was to be, for example, 6, that would be a corrupted vote. We would not have the actual decision that the majority wants. And this is what happens every day in distributed systems. Machines can crash, can have delays, can have network issues. There's a lot of issues that can happen. So in order to prove that it's not possible, I'll walk you through some definitions. And for that, let's recall the sentence that I've said before. No consensus can happen in an asynchronous system with one faulty process. To begin with, we need to define what consensus is. And what I mean by consensus is a process, an algorithm, can solve consensus when we say that it solves these 3 properties. First one being agreement. What I mean by agreement is if we have multiple processes, they should all agree on the same value. For the sake of simplicity and to show that even with the simplest values, we can prove FLP, we're going to take only binary values. So only 1 and 0 are possible. So to actually validate the agreement property, we need all the processes to agree on the same value. Say, for example, 1. The second property is the validity property. The validity property says that in order for the validity property to be achieved, all the processes have to at least choose one value that was suggested by one of the processes. So for example, to come back to our example earlier, we cannot go play football. That was we could all agree still on playing football, but that would not be one of the suggestions that of one of us. That would be a suggestion, an exterior suggestion. So this would harm the validity property. The last one is termination. And termination, like the name suggests, is that the algorithm has to terminate. It has to find a solution. It has to come up with an outcome, with an answer. It doesn't have to be correct, just have to be there. The algorithm that has to not halt. So now we defined what consensus is. Well, let's talk about an asynchronous system. To make it very simple, an asynchronous system in a distributed system, in a network, only means that every single process does not know about the state of the other. So we work in the assumption, and that's how the internet works, that no machine knows whether another process is slow or is dead, has crashed, is having network issues, electricity is not there. We don't know. We just assume that there's no time, there's no global clock, and we process messages when they arrive. If they don't arrive, we don't make an assumption on the other process. The last one is one faulty process, and that is a process that is crashed, just for simplicity. So there's a lot of formal definitions, but to make it quicker, I'm gonna actually explain them with an example to walk through them very, very simply. So we're going to describe adversary, valency, configurations, and for that, all of that to prove the FLP theorem that here suggests that if A is a consensus algorithm running on at least two asynchronous processes that we explained earlier, tolerating at most one crash failure, then there exists an admissible execution such that there is an infinite sequence and no configuration in the path is ever decided. I know this is very overwhelming for now, but let me walk you guys through it. So the first lemma that we need to prove in order to prove the theorem is that there exists a bivalent configuration. I know for now we don't know what a bivalent configuration is, so I'm going to explain it very quick. Let's say we have a system with 4 nodes. This is our graph, and it's a mesh. So every process can communicate with every process. Let's call this one 1, 2, 3, and 4. Now, let's introduce you to the concept of message system. So message system is a set that contains all the messages. It's all the messages in transit. What I mean by messages in transit is that messages that are being sent to a process but have not been received yet. So it's in transit. Let's, for example, give an example here. M1, M2 is sending a message to process, what is this, 4? Let's call this M2. And here, M3, process 1 is sending a message to the process 2. This is the message system. So it's the set of all messages that are being sent but have not been received yet. The second property, or definition, is a process. What is a process here? A process can be defined as a tuple of an input value, that is the suggestion. For example, in our example, the input values that we all had was either going to the cinema, going swimming, or having dinner. Here, for the processes, for simplicity's sake, the input values can only be 1 or 0. These can only be binaries. A decision output, or a decision state, that is the answer, that is the actual thing that we're looking forward for, is to give, for the processes to actually give an answer and agree on something, and an internal state that we represent as S. For the sake of simplicity, we're going to describe the internal state for being as the input and the value that the process is leaning towards deciding. So let's say I have process 1 has an input of 1, for example, 2 has 0, 3 has 0, and 4 has 1. And let's say the process 4 sends a message to process 1. The message could have some sort of information that's within the internal state, and it could change its mind and actually decide to be to have an internal state of 0. This is how the process of agreeing works. So actually not last definition that I'm going to give you is a configuration, and a configuration is a set of a pair of the set of internal states of all processes. We can describe this as a sort of vector that would look something like this. So for this example, process 1 has an internal state of 1, 2 has 0, 3 has 0, and 1 has 1. Plus the set of the message system. So it's the set of all messages. So here, for example, we have M1, M2, and M3. These are all the messages in transit. This is what we call a configuration. This is a way of describing the system and the state of the system. And then one last definition is a step. A step, we can think of it as an event, as a sort of function that can be applied on a configuration. It's something that happens within the configuration that could change the internal state of one of the processes, and that could change also the message system. So one step that could happen, for example, is for the message of, for example, the process 2 being sent to the process 4, and the step is defined as such. For example, it's the message and the process ID. So here, for instance, it would be M2, and the process would be 4. The 4 as the receiving of the message, and this could change the internal state of the fourth process. And instead of agreeing on 1, it would decide 0, for instance, and that would change the configuration from being like this to being like this. We call an algorithm successful once all values and all processes have agreed on a single value. So a configuration that would be successful should be looking something like a vector that looks something like this. Because everyone has agreed on the same value, and the messages would be an empty set because the messages have all been received. So now let's go a bit deeper and see the configurations as a graph. I can draw this for our previous example. If my example, I had 3 messages, and 3 messages could arrive in different orders. So if they can arrive in different orders, if they can arrive in different orders, we'd have different configuration depending on which message was processed first. So for message 1, we'd say this would take us to our configuration 1. Message 2, this would take us to our configuration 2. And message 3 would take me to our configuration 3. Now I'm going to introduce you to a new concept, a new definition, which is valency. Valency is sort of, to look at it in a simple way, what is the configuration leaning towards? We say a configuration is divalent when the configuration has as output, as possible outputs, either, so the set D. So for example, for instance, in our case, D is either 1 or 0. So we say it's divalent if it has the possible outputs as 1 or 0. And for this case, we call it bivalent. So for here, since the initial configuration can either take us to either a 1 or a 0, the processes could either agree on 1 or 0, we call this a bivalent process. When the configuration can only take us to one possible outcome, for instance here, to 0, regardless of how many steps has been applied on this configuration, we call it a univalent configuration, and here precisely a zero-valent configuration. And to make the graph simpler, we're not going to show the next one that comes after because they're all going to be zero-valent. Every single configuration that comes after a univalent configuration stays univalent configuration. So let's come back to our example here. We have a zero-valent configuration, another zero-valent configuration, and another one. A one-valent configuration, and bivalent configuration, which could take us to both. So this is a bivalent configuration because it could take us to either a 0 or to a 1. Now, if you understood correctly, an algorithm that runs successfully has to have univalent configuration as their leaves. What that means, a successful algorithm could take either path and still finish by agreeing on a value. What C being univalent means they agreed on one value. Here in this case, the configuration means all processes have agreed on the value 0. Here, all the processes have agreed on the value 1. So in order to have an algorithm that deterministically says that the consensus is possible, every single leaf of the graph have to be univalent. This is why I'm going to introduce you to a new concept, which here is going to be a critical configuration. A critical configuration is a configuration where, regardless of the step that happens afterwards, it would take us to a univalent configuration. For instance, this configuration over here is a critical configuration because it takes us to either a zero-valent configuration or a one-valent configuration, which are both univalent configurations. Now, to come back to our lemma, we need to prove that bivalency is even possible. To do that, we're going to represent the configuration this way, the same way I've showed you earlier. And let's assume all of these are one-valent configurations. Yeah.
I just had a quick question. Can you show us the lemma again?
The lemma. We have to show that a bivalent configuration where the processes are not deciding. So a bivalent configuration technically means that processes are not never deciding. We need to show that could exist in the first place. So to show that, let's represent the configuration this way and say that we have configurations coming from 0 to n. And let's assume that they're all univalent. So they're all either zero-valent or one-valent. And let's, for the sake of simplicity, we'll take it as a concept of majority. So the more zeros there are, it's going to be zero-valent. For this case, since they're all ones, it's one-valent, obviously. So here, if we notice, these are probably going to be zero-valent. And the closer you are to here, you're going to be one-valent, right? But this could say, we could say as well that there exists a CI where there's a switch, where one process decides whether this configuration is either zero-valent or one-valent. And here is the catch. If something happens to this process, let's say it crashes, we do no longer have the ability to communicate with this process. We now have two exactly similar configurations where this part is exactly as this part, and this part looks exactly as this one, but both of them are univalent in different ways. This one is zero-valent, and this one is one-valent. They cannot be both zero-valent and one-valent, therefore, they have to be both bivalent, and this is how we prove that bivalency is even possible. So this is the first step. We have shown the first lemma. The second one is saying, at any bivalent configuration, an adversary can always come in and find a step that makes the next configuration bivalent. What I mean by that, to come back to our graph, is that at any point where there is a bivalent configuration, and we're talking specifically about critical bivalent configuration because these are the most important one. We're looking at a graph to make the FLP work. We're looking at the critical ones. An adversary, what we mean by adversary is sort of someone who wants to ruin our algorithm. Let's look at it as the worst case scenario. There could always be something happening in this config where this would make it bivalent and therefore not deciding. So in order to show that, and we can clearly say here that, for example, if we see a tree, for example, that takes from non-critical to non-critical, infinitely, there's always a path where there's no decision made. So we need to get rid of all these decisions in order to prove that there's always a way of making a decision. So, for instance, let's take a critical. Let's take for example. Let's forget about this and take C as a critical